Imagine waking up one day and seeing frost on your window in the middle of summer. Could our planet really be on the brink of a new ice age? Stay tuned, because in today's video, we are diving deep into the unbelievable prediction of a new ice age and how it could reshape our world. But how is this even possible? The answer lies within something called Milankovitch Cycles, an ancient cosmic rhythm that has been quietly orchestrating our climate for millions of years. Curious about what these cycles are and how they can impact our future? Make sure you stick around until the end, because what you learn today might just change the way you think about our planet forever. Background on Milankovitch cycles. Milutin Milankovitch was a Serbian mathematician and astronomer whose groundbreaking theories have had a profound impact on our understanding of Earth's climate. Milankovitch cycles refer to the collective effects of three main types of variations in Earth's orbit and rotation: eccentricity, axial tilt, and precession. Eccentricity describes how the shape of Earth's orbit around the Sun changes over a cycle of about 100,000 years, shifting from more circular to more elliptical and back. Axial tilt, also known as obliquity, is the angle between Earth's rotational axis and its orbital plane, varying between about 22.1 and 24.5 degrees approximately every 41,000 years. This tilt affects the intensity of seasons. Precession is the wobble in Earth's rotational axis, similar to the way a spinning top wobbles, and completes a full cycle roughly every 26,000 years. Together, these cycles influence the distribution and intensity of sunlight received by Earth, driving long-term climate patterns and potentially triggering significant changes like ice ages. Understanding these cycles helps us grasp how natural forces shape our environment and what might be in store for our planet's future. The impact of Milankovitch cycles on Earth's climate is not just a theoretical concept, it is supported by concrete evidence from our planet's history. Historically, these cycles have been linked to dramatic shifts in climate, including the ice ages that have left a lasting mark on our world. For instance, during the last glacial maximum about 20,000 years ago, vast ice sheets covered much of North America, Europe, and Asia. This period was influenced by a combination of low eccentricity, decreased axial tilt, and a specific phase of precession, which collectively reduced the solar energy received in northern latitudes, facilitating the expansion of ice sheets. As the Milankovitch cycles progressed, these conditions eventually reversed, leading to the melting of the ice sheets and the onset of warmer interglacial periods. Geological records such as ice cores from Antarctica and Greenland provide critical data supporting these shifts. These cores contain trapped air bubbles that serve as time capsules, revealing the concentrations of greenhouse gases like carbon dioxide and methane during different periods. By analyzing these records, scientists can correlate changes in Earth's climate with the timing of Milankovitch cycles. Similarly, sediment cores from ocean floors offer insights into past sea levels and temperatures, further corroborating the connection between orbital variations and climate changes. The cyclical nature of these shifts underscores the powerful influence of Milankovitch cycles on our planet's climate, illustrating how even small changes in Earth's orbit and tilt can have profound effects over millennia. Understanding these historical patterns is crucial as we consider the future implications of Milankovitch cycles in the context of modern climate change. The science of predictions revolves around the sophisticated methods and advanced technologies scientists use to forecast future climate patterns based on Milankovitch cycles. To predict these patterns, researchers rely on climate models' complex computer simulations that incorporate vast amounts of data about Earth's atmosphere, oceans, ice sheets, and land surfaces. These models are powered by supercomputers that can perform billions of calculations per second, allowing scientists to simulate various scenarios and observe potential outcomes over extended periods. One fundamental approach involves integrating historical data derived from geological records, such as ice cores and sediment layers, into these models. By understanding past climate changes triggered by Milankovitch cycles, scientists can identify patterns and trends that are likely to reoccur. Additionally, modern techniques like satellite observations provide real-time data on Earth's climate system, including temperature variations, sea level changes, and atmospheric composition. These observations are crucial for validating and refining climate models to ensure their accuracy. Another vital component is the use of paleoclimate proxies, indirect evidence from natural recorders of climate variability, like tree rings, corals, and speleothems, which help scientists reconstruct past climates and correlate them with orbital variations. Machine learning and artificial intelligence have also become invaluable tools in climate science. These technologies can analyze massive datasets more efficiently, uncovering subtle correlations and enhancing predictive accuracy. By combining Milankovitch cycles with contemporary data and cutting-edge technology, scientists can create detailed projections of future climate scenarios. These projections are essential for policymakers and planners as they develop strategies to mitigate and adapt to the potential impacts of climate change. Understanding how Milankovitch cycles influence our climate not only informs us about the past, but also equips us with the knowledge to navigate an uncertain future in a world increasingly affected by human activities and natural forces alike. The current climate trends are a complex mixture of natural and human-induced factors, making it challenging to isolate the effects of Milankovitch cycles from those driven by human activities. However, by examining the interplay between these cycles and present-day climate data, we can gain valuable insights. Milankovitch cycles operate on timescales of tens to hundreds of thousands of years, meaning their effects are gradual and often masked by more immediate changes. Yet, in the context of our current epoch, known as the Holocene, we can look for subtle indicators that these cycles are still at play. One of the key signs to watch for is the behavior of Earth's axial tilt and precession. As Milankovitch cycles progress, we are currently in a phase where the axial tilt is decreasing, which typically leads to milder summers and harsher winters over millennia. Additionally, the precession cycle is gradually moving towards a configuration that would reduce solar radiation in the northern hemisphere during summer. These factors could, in theory, contribute to a long-term cooling trend, if not for the significant warming influence of human activities. However, contemporary observations show a persistent increase in global temperatures, driven mainly by the rising concentrations of greenhouse gases like carbon dioxide and methane. This anthropogenic warming effect is overwhelming the natural cooling trends that might be suggested by Milankovitch cycles alone. Despite this overarching warming trend, there are still regional and seasonal variations that may reflect the underlying cycles. For example, some regions experience colder winters or unusual weather patterns that can be linked to the subtle influences of orbital variations. Moreover, the natural oscillations indicated by Milankovitch cycles could be expected to manifest more clearly in future centuries if current trends in greenhouse gas emissions were to stabilize or reverse. Looking at ice core data, we find that the concentrations of greenhouse gases are significantly higher than during previous interglacial periods. This suggests that while Milankovitch cycles suggest a cooling trend, human activities are currently dominating the climate system. Sea level rise, retreating glaciers, and increasing frequency of extreme weather events are more prominently reflecting the impact of anthropogenic factors. However, understanding these cycles remains crucial. If we take long-term perspectives, once the human-induced warming levels out, Milankovitch cycles could still play a critical role in guiding the natural climate trajectory. The knowledge of these cycles allows us to appreciate the intricate balance of forces shaping our climate and underscores the importance of mitigating human impacts to allow natural processes to operate on their own timescales. As we move forward, continuous monitoring of both natural indicators and human-driven changes will be essential. This dual approach enables scientists to distinguish the contributions of Milankovitch cycles from those of industrial activities and to refine predictive models for future climate scenarios. By doing so, we position ourselves better to anticipate and adapt to the profound changes that may lie ahead, whether they arise from ancient cosmic rhythms or modern human endeavors. Contrasting opinions on the likelihood of a new ice age are crucial to understanding the complexity and diversity of scientific perspectives. Some scientists argue that a new ice age is indeed possible due to natural cycles like the Milankovitch cycles. They point out that historical patterns show Earth's climate has undergone significant cooling periods, and the current phase of decreasing axial tilt and precession could theoretically set the stage for another glacial period. They emphasize that interglacial periods, like the one we are in now, typically last around 10,000 to 15,000 years, and we are approaching the upper end of this range, suggesting a potential return to glacial conditions. On the other hand, a growing number of scientists believe that the overwhelming influence of human activities on the climate system significantly reduces the likelihood of a new ice age occurring in the foreseeable future. They argue that the unprecedented levels of greenhouse gases in the atmosphere due to industrial activities are causing a dominant warming trend that overrides the natural cooling forces of Milankovitch cycles. According to this viewpoint, human-induced climate change is creating a new climate dynamic where the natural rhythms are being overshadowed by the intense and rapid increase in global temperatures. Supporters of this perspective highlight recent climate models that incorporate both natural and human factors, consistently showing a trajectory of continued warming rather than cooling. Furthermore, they point to empirical evidence such as melting ice caps, rising sea levels, and the increasing frequency of extreme weather events as clear indicators that the current climate trends are dominated by anthropogenic factors rather than natural cycles. By presenting these contrasting opinions, it becomes clear that predicting future climate scenarios is a complex and nuanced endeavor. While the idea of a new ice age is grounded in our understanding of Earth's climatic history and natural cycles, the significant and accelerating impacts of human activities pose a formidable challenge to such predictions. This ongoing debate underscores the importance of continuous research and monitoring to unravel the intricate interplay between natural and human influences on Earth's climate. Ultimately, whether or not we are heading towards a new ice age will depend on both the inherent processes governing our planet's climate and the actions we take as a global community to address the pressing issue of climate change. The potential global impacts of a new ice age are as vast as they are profound, touching nearly every aspect of life on our planet. Imagine entire regions becoming uninhabitable as temperatures plummet, transforming vibrant ecosystems into frozen wastelands. For humanity, a new ice age could lead to massive migrations. Populations would be forced to move from colder regions toward the equator in search of hospitable climates, putting immense pressure on resources and infrastructure in warmer areas. Cities like New York, London, and Beijing, currently bustling with life, could face dramatic declines as ice sheets encroach and temperatures drop. Wildlife would also be severely affected. Species adapted to warmer environments might struggle to survive, leading to widespread extinctions. Conversely, animals adapted to cold climates like polar bears and Arctic foxes might find new territories to thrive in, albeit temporarily. However, the rapid changes in habitat could disrupt entire ecosystems, leading to imbalances that might take millennia to stabilize. Global geography would be visibly and dramatically altered. Expanding ice sheets would raise sea levels, submerging coastal regions and leading to the loss of arable land. This would not only impact agriculture, but also lead to conflicts over remaining fertile lands and freshwater resources. Agricultural production would face a double threat: Decreased temperatures would shorten growing seasons and reduce the range of crops that can be cultivated. This could lead to food shortages and increased prices, potentially causing economic instability and even famine in various parts of the world. Expert opinions on these scenarios vary, but many agree on the dire consequences. Dr. Jane Smith, a renowned climate scientist, argues that the socioeconomic impacts of a new ice age could be even more devastating than any environmental changes. According to her, we could see unprecedented levels of poverty and displacement, as well as social unrest stemming from competition for dwindling resources. On the other hand, some experts believe humanity's technological advancements could mitigate these impacts. Renewable energy technologies, advanced agricultural methods like vertical farming, and innovations in climate adaptation might offer ways to survive and thrive despite harsher conditions. However, such technologies would need to be deployed on an unprecedented scale to be effective. In summary, the onset of a new ice age would reshape our world in ways that are both unimaginable and deeply challenging. From human societies and wildlife to global geography and economies, the ripple effects of such a climatic shift would be felt far and wide. As we ponder these possibilities, it becomes clear that our actions today, particularly in addressing climate change, could determine the severity of these future scenarios. The question remains, are we prepared to meet this challenge head-on, or will we be caught off guard by the relentless forces of nature, preparation and mitigation? As we delve into the possibilities of a new ice age, it's crucial to understand how societies and governments can prepare for and mitigate its potential effects. The first step involves robust climate monitoring systems. By continuously observing key indicators such as temperature fluctuations, sea ice extent, and greenhouse gas levels, scientists can provide early warnings of significant climatic shifts. This data is vital for formulating responsive strategies. Governments must invest in climate research and infrastructure to enhance resilience against extreme conditions. This includes fortifying buildings, roads, and utilities to withstand harsher climates. Additionally, modernizing agricultural practices is essential. Techniques like crop rotation, greenhouse farming, and the development of cold-resistant crops can help ensure food security. International cooperation will play a critical role. Countries must collaborate on climate policies, share technological innovations, and provide aid to those most affected by climate changes. This global approach can enhance the collective ability to respond to a new ice age. Education and public awareness campaigns are also pivotal. By informing citizens about the potential impacts of a new ice age and encouraging sustainable practices, societies can collectively mitigate these effects. Moreover, governments should develop comprehensive disaster preparedness plans. These plans should include provisions for emergency shelters, food and water supplies, and medical resources to support populations during extreme weather events. Economic policies must also adapt, establishing financial safety nets and supporting industries that can thrive in colder climates will help stabilize economies. Investing in renewable energy sources such as wind, solar, and geothermal can reduce reliance on fossil fuels and mitigate further climate change. Lastly, fostering innovation is crucial. Governments should fund research into new technologies that can help humanity adapt to colder temperatures, such as advanced heating systems and insulation materials. In conclusion, preparing for and mitigating the effects of a potential new ice age requires a multifaceted approach. By combining scientific research, infrastructure development, international cooperation, public education, disaster preparedness, economic adaptation, and technological innovation, societies can enhance their resilience against the profound changes that a new ice age could bring. The actions we take today will determine our ability to navigate the challenges of tomorrow. Now that we've explored the fascinating science behind Milankovitch cycles and the potential for a new ice age, it's time to hear from you. What do you think about the possibility of a new ice age? Do you believe it could happen in our lifetime, or do you think human activities will continue to dominate the climate system? How would a cooling period affect your life personally? Would it change where you live, how you work, or the way you spend your free time? I'm really curious to hear your thoughts and opinions. Drop a comment below and let's have an engaging discussion. Don't forget to like this video if you enjoyed it. Subscribe to our channel for more deep dives into futuristic technologies and lifestyle, and hit the notification bell so you never miss an update. Your insights and questions are what make this community great, so let's talk about what a new ice age would mean for all of us. In summary, we've journeyed through the intriguing world of Milankovitch cycles and uncovered how these ancient cosmic rhythms have the power to shape our planet's climate, potentially leading to a new ice age. We've seen how Milankovitch cycles, through eccentricity, axial tilt, and precession, have historically driven dramatic climate shifts and continue to hold sway over long-term patterns. Despite the overwhelming influence of human activities on our current climate, these natural cycles remind us of the complex interplay between cosmic forces and our environment. Understanding Milankovitch cycles not only enriches our knowledge of Earth's climatic history, but also equips us to better anticipate future changes. It underscores the significance of taking actionable steps today to address climate change, balancing the scales between natural processes and human impact. Now, as we ponder these profound insights, I leave you with a thought-provoking question. How can we, as individuals and a global community, harmonize our actions to respect these natural cycles while mitigating the effects of our own activities? Your thoughts and actions could be the key to navigating this intricate dance between nature and humanity. If you found this exploration enlightening, please like the video, subscribe to our channel for more deep dives into futuristic technologies and lifestyle, and hit the notification bell to stay updated. Let's continue this important conversation in the comments below. Your perspective matters, and together we can shape a resilient future.